Okay, dear colleagues, let's start in time today. First of all, I would like to announce next seminar. So next week, we will have a talk from Sergey Vichanin, who is a member of our Quantum Technology Center, and also he is a member of LIGO Scientific Collaboration, and he will talk about quantum correlations between light and the kilogram mass mirrors of LIGO. Actually, this work has been recently reported in Nature, so he will give a report about this paper. Okay, and now our speaker is Ilia Luchnikov from Moscow Institute of Physics and Technology, and also from Scoltech, and he will talk us about Riemann optimization for quantum technologies. Please.
Thank you, Konstantin, for introduction. First of all, I would like to thank all organizers for the given opportunity to have a talk here. It's a big pleasure for me. And today, as Konstantin said, I'm going to talk about Romanian optimization for quantum technologies, and in particular about our open source implementation of that methods, optimization methods for quantum technologies, which is called QGOpt. So first of all, let me introduce the team of QGOpt contributors. Starting from the left, it is myself, then Alexander Ryzhov, who is a postdoc from engineering track of Skolkovo Institute of Science and Technology, and Misha Krechitov, who is a PhD student of engineering track of Skolkovo Institute of Science and Technology. And before diving deep into Riemannian optimization, let me remind you about what constraint optimization is and why it is so important, not only in different engineering directions, but also in quantum technologies. Let us consider a standard constraint optimization setting. We have a function f of x, where x is a vector from n-dimensional Euclidean space from Rn, and we want to minimize this function with respect to x. Besides that, we have set of equality and inequality constraints that should be preserved during the optimization. And in the sketchy picture below the equation, I represent function f by set of levels and constraint, a set of constraints by blue curve. And we want to find a point from this blue curve that returns minimal value of f of x. So many different problems of quantum technologies can be formulated in terms of constraint optimization. Let us consider several examples. Let's start from quantum state tomography. With a given set of measurement outcomes that came true, one can find the most probable density matrix by maximizing the following likelihood function. But we have to keep in mind that density matrix should be non-negative, and trace of this density matrix should be equal to 1. So one can see that it is a classical example of constraint optimization. Another frequently used example is quantum channel tomography. So again, we have a set of measurement outcomes came true. We have initial density matrices which we passed through a channel, and we have matrix C, which is a Chern matrix that parameterizes a unknown quantum channel. And by maximizing this logarithmic likelihood with respect to Chern matrix, we can find the most probable quantum channel. And again, we have constraints. First constraint is the following. Chern matrix should be non-negative. It means that the corresponding quantum channel is completely positive. And partial trace of Chern matrix should be equal to identity matrix. It means that the corresponding quantum channel is trace preserving. Another big set of problems that can be formulated in terms of constraint optimization is the following set. It is quantum control, state preparation, quantum gate decomposition, integramentary normalization, and etc. So all these problems can be formulated as optimization of some loss function, which is function of set of isometric and unitary matrices. And we want to minimize this loss function with respect to this set of matrices. And of course, since we are talking about isometric and unitary matrices, all these matrices have the following orthogonality constraints. So of course, the set of problems of quantum technologies that can be formulated in terms of constraint optimization is not restricted only by these 3 examples. We can formulate many others applications. And the important thing here is that some of these constraints take form of smooth manifolds, or in other words, smooth multidimensional surfaces. So let me give you not rigorous definition of embedded Riemannian manifold. So let us consider some n-dimensional Euclidean space and set of equations that defines a subset of this Euclidean space. And if Jacobian of this set of equations has full rank everywhere, then this set of equations defines a smooth manifold or a smooth multidimensional surface. Having constraints in the form of a smooth manifold, one can turn from optimization in the Euclidean space with constraints to optimization on a Riemannian manifold without constraints. In other words, instead of walking along Euclidean space, we can Euclidean space with preserving of constraints, we can walk along a Riemannian manifold. So we have to generalize gradient-based optimization methods that we use in Euclidean space on the Riemannian case. And let us start from the gradient. Gradient is the central object of all gradient-based optimization methods. In the simplest case of gradient descent, we usually move a point along the gradient or in the opposite direction. But if we have some embedded Riemannian manifold that is some smooth surface embedded into Euclidean space, and we have some point and gradient of function of f of x, which is drawn from this point. Of course, it is quite clear that we cannot move our point along this gradient vector in the opposite direction, because it takes our point out of a manifold. So we can, for any smooth manifold, we can introduce the notion of tangent space. Any point of a manifold has tangent space. Tangent space is a union of all possible tangent vector drawn from a point x. And intuitively, it is very clear that Riemannian gradient generalization of Euclidean gradient on the Riemannian case should lie completely in tangent space. So if our Riemannian manifold inherits Euclidean metric from a total Euclidean space, then Riemannian gradient can be calculated very simply. It is orthogonal projection of the Euclidean space on the orthogonal projection of the Euclidean gradient on the tangent space of a point x. So usually it is very simple and computationally efficient procedure. So another important object we should be generalized on the Riemannian case is the notion of straight line. If we walk across some Euclidean space, we can take steps in the direction of straight lines. However, since in the Riemannian case we have multidimensional manifolds, multidimensional surfaces, we cannot go along straight lines, because it takes our point out of a manifold, and we should generalize the notion of straight line on the Riemannian case. But let us start from the Euclidean case. Let me remind you what is straight line in Euclidean case. Assume that we have some initial point, which is represented here by red ball, with initial coordinate x of 0. And we push this point with initial velocity v. Then we wait for some time t and end up with a new point x of t. So it is a straight line in Euclidean case. However, in Riemannian case, we have a different kind of intuition about straight line. Let us consider again some initial point, which is represented again by red ball here with initial coordinate x0, and let us imagine that this point is restricted by two smooth surfaces that are very close to each other, and this point can move only in between these two manifolds, two surfaces. We again push this point with initial velocity v, wait for some time t, and end up with a new point. And this curve, which lies completely in a manifold, is called geodesic, and it is generalization of straight line on the Euclidean, on the Riemannian case. However, from the computational viewpoint, very often geodesic is very computational demanding. It requires too much computational efforts. Instead of geodesic, one can use retraction. Retraction is also a curve that lies completely in a manifold, but the ending point of this retraction can be different, and this difference is approximately equal to some constant multiplied by v squared t squared. In other words, retraction is a first-order approximation of geodesic. And of course, retraction is not unique. There are infinitely many retractions, and usually one can choose computationally efficient, computationally cheap retraction and practicals that can be used in different Riemannian optimization techniques. So the third important notion that we need to generalize on the Riemannian case is a notion of vector transportation. How so we have to understand how can we transport tangent vector along a manifold. Let us consider some initial point here, which is represented by red ball again, and some tangent vector W here. And let us assume that we want to transport this vector along another tangent vector V. How can we do that? First of all, we can make a retraction of our initial point and end up with new point, which is represented here by blue ball. Then, since we are working with embedded manifolds, vector W is a vector from tangent space, but it is also vector from total Euclidean space. We can simply make a parallel transport of this vector from initial point to from an initial point to a new point. But then, since this is a smooth manifold and it can be curved, in general case, vector W doesn't lie, no longer lies in the new tangent space, in the tangent space of a new point. So how can we fix this situation? We can simply take an orthogonal projection of vector W on the new tangent space. And this is the simplest implementation of vector transport on a Riemannian manifold that is practical and usually cheap from numerical viewpoint. So now let us consider example. The simplest Riemannian manifold is a one-dimensional circle that is embedded into two-dimensional Euclidean space. And let us assume that we have some initial point x on this circle, and we want to move this point along some vector ux. How can we do that? Since this S2 is embedded manifold and we have two-dimensional Euclidean space, and x is not only a point from this manifold, it is also a vector from total Euclidean space. And we can simply take a sum of these two vectors, x and u. Then, of course, the result of this summation doesn't lie in the manifold, and we have to project it somehow back to the manifold. How can we do that? We can simply divide the result of this summation by the length of this resulting vector, and we end up with a point from the manifold. One can show that it is a first-order approximation of geodesic. In other words, it is a retraction, and this procedure can be used in different Riemannian algorithms, and it is numerically efficient. And here I'm not going to consider vector transfer because here it is trivial. So of course, all the stuff I was talking about is not rigorous, and if you want to have a deep mathematical introduction into the topic, you can read the following two books written by experts of the field of Riemannian optimization. But now let us go a little bit closer to the applications. Let us understand how can we generalize first order optimization methods in Euclidean space on the Riemannian case. Let us consider the simple example of standard of gradient descent with momentum. Let us have a look on the left part of the slide. Here you can see the iterative scheme that represent gradient descent with momentum. So at first, we calculate a so-called momentum vector, which is a weighted sum of the previous value of momentum vector and gradient in the current point. And then we make a step towards or in the opposite direction in this particular case, because here we assume a problem of minimization of some function. We take a step in the opposite direction of the momentum and get a new point. So now let us understand what kind of difference we have with Riemannian version of this gradient. Let us have a look on the right part of this slide. So the first important difference here, you can see that instead of Euclidean gradient, we use Riemannian gradient, which I've just covered several slides ago. Then we have intermediate momentum vector, which here is represented by m with tilde. So the second important difference here is that instead of step towards some straight line, we here use step according to retraction, some retraction mapping. And also in the Riemannian case, we have a third step, which is vector transport of intermediate momentum vector to the new point. So why we need to perform this vector transport? Since we make a step to a new point, ex t plus 1, and since our we are talking about smooth manifold, the tangent space of a new point can be different in comparison with the tangent space of a previous point. And then we have to perform vector transport instead of trivial parallel transport in the Euclidean space. So it is pretty general scheme, and if you want to read more about such kind of generalization of methods, optimization, first order optimization methods from Euclidean space on the Riemannian case, you can read the following two papers. So now let us go a bit closer to applications. Now I'm going to talk a little bit about Riemannian manifolds that emerge in quantum mechanics and quantum technologies, and about Riemannian manifolds that are implemented in our open source library. So the first manifold is so-called Stiefel manifold. It is a set of all possible, sorry, do we have question? Sorry, I'm sorry. It is a set of all possible isometric matrices of fixed size n by n. This manifold can be used for quantum control, for integramentary normalization, for quantum state preparation, and so on. So another important manifold here is manifold of positive semi-definite matrices of size n, manifold of density matrices of size n, manifold of Choi matrices, manifold of POVMs with fixed number of elements and fixed size of Hilbert space, and manifold of Hermitian matrices. All this manifold is implemented in our library and can be used for different optimization purposes. So also in our library, we have the following set of first order optimization algorithms that are implemented. And also it is very important question to discuss is complexity of different building blocks of optimization algorithms. Any first order optimization algorithm on a Riemannian manifold includes retraction, sometimes vector transport, projection, and calculation of Riemannian gradient. And here you can see the table of complexity of all these building blocks for different manifolds we have in our library. So now let us turn to the practice, and let us consider use cases of Stiefel manifold. If you want to read more about use cases of Stiefel manifold, you can read our recent preprint. You can find it in archive, and preprint of our colleagues that appeared in archive 4 days after we submitted our preprint. The first interesting example is integramentary normalization. Assume that we have some many-body quantum system. For simplicity, let's say that this many-body quantum system is a quantum spin chain, and this physics of this quantum spin chain is described by a local Hamiltonian. In particular, here we consider transverse field Ising model with periodic boundary conditions. And let's say that we want to find ground state and energy of its ground state. We cannot find energy of ground state directly via straightforward calculations because of curse of dimensionality. Dimensionality of Hilbert space grows exponentially with number of particles. However, we can use some renormalization techniques. We can reduce dimensionality of a Hamiltonian and diagonalize it numerically. So here we consider a particular renormalization scheme, which is called integramentary normalization. It is based on so-called multi-scale integramentary normalization ansatz, which is a very specific tensor network that contains many unitary and isometric matrices. And therefore, it is a problem for optimization of Stiefel manifold. So here we perform such an optimization and, for example, found energy of ground state of this Hamiltonian. Let's have a look on the plot on the right side of the slide. Here you can see how difference this delta E is a difference between exact ground state energy of this spin chain and a ground state energy found by integramentary normalization and optimization on the Stiefel manifold. One can see that this difference drops rapidly up to 10 minus 5 with number of iterations, and we found ground state energy with quite high accuracy. And let us have a look now on the left side of this slide. Here you can see how difference between energy of first excited state and ground state energy depends on external magnetic field. It is important to note that this Hamiltonian, multidimensional many-body Hamiltonian, has quantum phase transition for external magnetic field Hx equal to 1. And here you can see typical behavior of the gap in such a system with quantum phase transition. So to conclude, one can see that optimization of Stiefel manifold can be used for analysis of many-body quantum systems and phase transitions. If you want to read more about integramentary normalization, you can look through papers by Glenn Evenbly and Geoffrey Vidal, and in particular through this paper I have in the slide. So another interesting problems that can be solved by using optimization of Stiefel manifold is gate decomposition. We can decompose many qubit gate into the sequence of local gates and C-nodes. In particular, here we consider simple example of two qubit gate. It is known that any 2-qubit gate can be decomposed into the following sequence of local unitary gates and C-node. In total, we have 3 C-nodes and 4 layers with local unitary gates. So how can we decompose arbitrary unitary 2-qubit unitary gate into the following scheme? We can, for example, apply our minimization technique on Stiefel manifold and minimize Frobenius distance between desired quantum gate and its decomposition. I'm sorry, here we shouldn't have Frobenius distance in square. It's just a Frobenius distance. One can see that Frobenius distance between true gate and learned gate drops rapidly with number of iteration and achieves 10 minus 10. So eventually we have proper decomposition of 2-qubit unitary gate. So another example of application is state preparation. So here we consider the following simple example. Initially, we have a set of qubits, each of them in excited state, and then we apply some unitary circuit. And at the end of this unitary circuit, we want to have some desired quantum state. So we can, again, using optimization on complex Stiefel manifold, we can adjust all local unitary gates here and get a proper unitary circuit that provides us with desired quantum state. How to optimize this scheme? For example, we can optimize infidelity between output state and desired state. On the right part of this slide, you can see how infidelity drops with number of iteration up to 10 minus 15. So at the end of this procedure, we have proper unitary circuit for quantum state preparation. Another example of state preparation.
Sorry, we have a question from Stanislav.
Just a moment. Let me just look it.
I actually had a question about the slide about the spin chain. If you can hear me.
Yes.
The convergence of the algorithm looks a bit strange. So there should be some specific step in the algorithm which causes these bumps in the.
Yes, I can explain. I can explain why we have these artifacts here. So here we use so-called Adam optimizer from deep learning, Riemannian generalization of this optimization scheme, and this optimization scheme includes so-called momentum. I already discussed generalization of gradient descent with momentum on the Riemannian case, and because of this momentum vector, it is exponential moving average of all previous gradients. At the intermediate steps, it can be not optimal, but in total, this procedure leads to a good local minima. So is it clear?
So it doesn't correspond to some particular step like a projection or something.
Could you please repeat? Because
it doesn't correspond to some specific.
No.
Like a projection or.
No. It is because of momentum. Intermediate steps can be not optimal in this scheme. But it introduces to the optimization scheme acceleration. So is it clear? Can I go further?
Yes, thank you.
Okay. So now let us talk about another example of state preparation. Here we have spin chain with all spins in excited state, and we apply some unitary circuit. And in the end of this circuit, we want to have a maximally entangled quantum state. So how can we solve this problem? For example, we can maximize entangled entropy at the end of this circuit via Riemannian optimization. And on the left of this slide, you can, on the left side of this slide, you can see how a difference between exact maximal entropy and entropy obtained by applying this unitary circuit drops with number of iteration, and at the end we have a proper unitary circuit for preparation of maximally entangled quantum state. So now let us turn to use case of density matrix manifold. So the most transparent use case of density matrix manifold is quantum state tomography. So here we have an example of quantum state tomography. We have data set with 600,000 measurement outcomes, and we use tetrahedral POVM to perform measurements. And here you can see how trace distance between reconstructed, unknown and reconstructed states drops with number of iteration, and we have proper quantum state tomography. Let us discuss use case of Cherry matrices manifold. Again, the most transparent use case is tomography of quantum channels. Here we again have 600,000 measurements, measurement outcomes. We have tetrahedral POVM, and we have random input states that we pass through the unknown channel. And here you can see how it is not a trace distance; it is trace distance divided by number, divided by dimensionality of a Hilbert space. The physical meaning of this object is maximal probability to distinguish quantum channels. In this case, reconstructed quantum channels and unknown quantum channels. And you can see that this probability drops rapidly with number of iteration, and at the end we have proper tomography of quantum channel. So use case of POVM's manifold. How can we use POVM's manifold in quantum technologies? For example, we can use optimization techniques on them to find the optimal measurement scheme. In particular example, we validate this application. It is known that for a qubit if we don't have any prior information about quantum state of qubit, the optimal POVM that returns minimal variance of posterior distribution is tetrahedral POVM. So we can check it numerically using our scheme in order to validate our optimization on POVM's manifold. So we perform optimization and end up with the following intersection matrix between different elements of POVM. And one can see that it matches almost perfectly with analytical result for tetrahedral POVM. So actually we found tetrahedral optimal in theory POVM. We have small numerical noise here due to we represent posterior distribution as set of samples from uniform distribution across all possible density matrices. So we can go even beyond optimization techniques on Stiefel manifold. We can implement sampling algorithms on different manifolds, like Hamiltonian Monte Carlo on a manifold or Langevin dynamics on a manifold. And in this particular case, we consider example of Bayesian state tomography. Instead of maximization of logarithmic likelihood, here we sample from posterior distribution for different sizes of data sets. For n equal to 20 to 100, 1,000, 10,000, and 100,000 samples. And you can see that it looks like a proper quantum tomography, Bayesian quantum tomography. We have an experimental implementation of manifold Langevin dynamics in our library QGOpt, and all these results obtained by application of manifold Langevin dynamics to the manifold of density matrices. So if you want to get familiar with our library, which is written on top of TensorFlow, you can go to our documentation to quick start and read the code, go through the code, and also you can go through several tutorials that can be also found in the documentation of our library. So to wrap up, let me summarize possible applications of Riemannian optimization techniques to quantum technologies. these optimization techniques can be used for machine learning with unitary tensor networks, for quantum control, model identification, tomography of states and channel, many-body systems, and quantum phase transition. Probably it can be applied for adaptive quantum tomography because we can combine Bayesian tomography based on sampling algorithms on manifold and optimization over POVMs. And also we can implement, since TensorFlow is very flexible library for deep learning, and we can simply put together several manifolds and design some kind of very complicated networks. We can build combinations of approaches like in deep learning and optimize very complicated networks. Again, two links on our project. The first link is a documentation of our project, and second link is the repository or GitHub repository of our project. And that's it. Thank you for your attention. If you have any questions, I would be glad to answer them.
Thank you so much for an interesting and I hope useful talk. So please, questions.
I have a question.
Yeah, please.
Okay. So thank you for the seminar. It's a bit hard for me to follow, very mathematic stuff. But so I have a question in the sense, could you please tell a little bit more about the comparison between this Riemannian optimization and other kinds of optimizations? It was not very clear for me in which sense this is better than the other ones.
Yes, I can answer this question. Actually, we have not performed direct comparison yet, but we have some intuition why this method sometimes better than other methods. So first of all, a standard approach to constraint optimization is, let's say, interior point method, which is first of all second order optimization method. Sometimes, for example, if we optimize, let's say, if we try to find a ground state of many-body quantum system, this tensor network here we want to optimize includes a lot of different matrices, and it is completely impossible to apply second order optimization methods here. Also, interior point method, during the optimization, you should relax your boundaries and somehow perform optimization several times. It is a little bit longer than Riemannian optimization, I guess. I'm not an expert in interior point method, but I feel here that for kind of huge scale problems, Riemannian optimization seems to be better because it is cheaper. And also here we mostly, for example, in this particular case of integramentary normalization, we talk about not convex problem. Here we implemented optimization methods from deep learning which are aimed on non-convex, some kind of heuristical optimization of non-convex heuristical solution of non-convex problems. And here we have the same, very similar to neural networks example of non-convex optimization problem. So is it clear what I'm talking about?
So you mentioned convexity. It would be the second question, because it seemed to me when you mentioned that the manifolds were smooth, that the method would not be applicable to non-convex problems.
Actually,
is it? Yeah, and the second point is that you did not mention application in determination of separability of multidimensional system, which is a non-convex problem, I guess.
Actually, in this field of Riemannian optimization, there is a very big theory about what kind of problems can be solved by Riemannian optimization with mathematical guarantees and what kind of problems cannot be solved or can be solved but without any mathematical guarantees. And we didn't touch this because it is a very big field. So here's the philosophy of this approach is like in deep learning. We can try to solve any kind of problem, but we don't have guarantees. And if we can't solve, so then it is cool, we can use it in practice. If we have some problems, then we have to think more, probably have to implement more advanced optimization algorithms and so on. Honestly speaking, now I cannot answer fully on your question about convexity because especially in Riemannian optimization topic, it is really complicated mathematical theory. And I am at the beginning of this theory. So it is too difficult for me because I am a physicist, I'm not a mathematician. And so it is difficult.
Okay, just one last question. In this slide, you're showing now about this complicated Hamiltonians with lots of spins, etc. Is it correct to think that I understood correctly that this is a short-range interaction Hamiltonian? And if yes, would you be able to use the method for long-range interactions Hamiltonians, for instance, atoms in optical lattices with long-range interactions?
So yes, it is a local Hamiltonian. It means that we have interaction only between neighboring spins. However, this particular example, for example, for some values of hx, we have actually we have quantum phase transition. That means that in this point, when hx equal to 1, we have polynomial two-point correlation functions. Actually, we have very long correlations in this spin chain. In this sense, yes, we can use this method. And of course, it is here we just applied another version, another optimization technique to the well-known integramentary normalization problem. Usually, integramentary normalization problem is solved by so-called Evan-Blevidal optimization algorithm, but we just applied another simpler algorithm, much simpler for implementation. Actually, to implement Evan-Blevidal optimization algorithm, it requires, I don't know, probably weeks, several weeks. To implement our approach, it requires a couple of hours. It is very simple in code. It is very simple to implement. And of course, sorry, this method can be used to describe long-range effects in many-body cavity models.
Okay. So thank you.
Okay. Other questions, please?
Can I ask one question about this spin chain? Have you used it as a toy model for your renormalization procedure? Because this model is exactly solvable by Wigner-Jordan transformation, and you can find all the correlation functions, all the spectrum. Yes, it is a toy model, and you compare your normalization procedure with the exact results. Is it true? Yes.
Exactly.
Thank you.
We use this model because it is exactly solvable, and also it has quantum phase transition. I skipped unfortunately this thing, but integramentary renormalization has this advantage that it can describe quantum phase transition. For example, in another types of tensor networks like matrix product state cannot describe quantum phase transition, but integramentary normalization can. And here it is. We want to have simple, exactly solvable, many-body, strong correlated quantum system with phase transition. And this is exactly the simplest one is transverse field Ising model. But of course, we can apply this method to many others, not solvable models.
Thank you.
Stanislav?
So let me ask about the Bayesian tomography. So did you try to go to higher dimensionality, and how far can you go?
Yes, actually, we have not tried yet because I generated this picture yesterday. I've just made this manifold management dynamics in QG in our library. But I believe that, of course, we can also apply this Bayesian tomography to quantum channels. I expect that it should scale very well with dimensionality. Here, it is just a toy example. I put it here in order to just show that it works, and that's it. But I expect that it scales very well. But I need to check it. It is not yet validated for larger quantum systems.
Yeah, it would be very interesting. So if it really scales favorably, just let us know. Maybe we can.
Yes, it is a question of further development of this approach, and if you want, we can even collaborate, because I know that you do some adaptive, Bayesian adaptive tomography. Am I right?
Yes, here is, I think, Gleb Strucharin, who is
Yes.
a big specialist on Bayesian methods in tomography. So
Yes, it is second step. Oh, it is the next step.
So yeah, let's just discuss. Maybe we can find something.
Yeah.
Okay, great. Any other questions? Maybe our TIAN colleagues, Yuri Bogdanov, Boris Bantesh. Okay, if there are...
Thank you very much. Very nice talk. Very
Thank
nice.
you.
Very nice topic. A very good introduction to Riemannian geometry and a good description on the relationship between Riemannian geometry and quantum theory, I think. I would like only to draw Ilya attention to Chintsov's work on the connection between Riemannian geometry and mathematical statistics. Do you know about works?
No. I haven't heard about this work. Could you please send the name of this author through the chat of Zoom?
Okay. There is some mathematical book in Russian and in English also on this matter. Okay.
Okay, thank you very much for this information. I will definitely read this book. Thank you.
Okay. Thank you. Very good topic. Very good. Okay. Thank you.
Okay, any other questions, opinions? Okay, if not, let me thank again our speaker for a very interesting talk, and also I think it will be very useful. And see all of you next week at our next seminar. Bye.
Thank you. Goodbye.
Bye. See you soon in our meeting, right?
Yes.
Okay.